Hello, and welcome to Physics for Play. Today we're going to look at how to solve the harmonic oscillator equation using the differential equation solver in Mathematica. Let's get started. So in our last video, we solved the differential equation for a harmonic oscillator using the guess and check method, where we guessed a solution, we plugged that solution into the differential equation. We showed, after simplifying the algebra, that that equation was true under certain conditions. And then we made some animations and plots for the equation. That's great, but that was a lot of work. And it turns out there is a simpler way to do that in Mathematica using a differential equation solver called DSolve. So we're going to do that today. So to start with, I am going to take my differential equation, and we're going to solve that by wrapping that in a function called DSolve, capital D, capital S. And DSolve is a differential equation solver, which will solve for the function x as a function of time. So I've got three inputs here. I've got the equations I want to solve, the functions that are in that equation that I want to solve for, and the independent variable t. Now, when I run this, you can see very quickly, I don't even have to guess, it will tell me what that solution is. Here it's telling me x is a function, it's a function of t, and this is that function of t. Now, if we go back to our previous work, where we made a guess, you could see that was one of our guesses. That was guess number 3 here. It was just a constant times a cosine function times plus another constant times a sine function. That's exactly what we have here. Constant times a cosine function, another constant times a sine function. You will notice that unlike my ansatz, it does not have an omega in it. I did not give it an omega to start with. My initial differential equation has no angular frequency in it, but it automatically solves the angular frequency you need. So you've got a square root k over m here, which was the criteria that we identified needed to be true for this equation to work. So that's pretty much all there is to doing DSolve if you want to keep things as basic as possible. But we're going to make things a little bit more interesting because now I want to solve with some initial conditions. It helps if I spell initial right. There we go. So I'm going to take the same DSolve that I solved before, and now I'm going to give it a list of equations I want it to solve for. So I'm going to give it the original differential equation, mass times the acceleration, x double prime, equals minus kx. And I want to give it some initial conditions associated with that. So I'm going to give it an initial position. And I'm going to say that my initial position, so this is x at time t equals 0. I'm going to say that is going to be equal to x naught. And let me define what x naught is. Actually, let me leave x naught undefined since we can do this in symbols here. And I'm going to say my initial velocity, x prime of 0, is going to be equal to v naught. Equal to v naught. And you can see it automatically solves that, and it plugs my initial conditions in. So I can see what the solution is readily with those initial conditions. I want to use this later, so I'm going to define this to be a variable, which I'll call SOLN, solution. And I'm going to go ahead and plot my solution. So I need to give it some initial value. So I'm going to say k is 1. I'm going to say k is 1. I am going to say m equals 2. Again, you put the semicolon in at the end there if you don't want it to output the results. I'll say x naught is 1. I'll give it, I'll start it at rest, so no initial velocity. And I'm going to plot x of t we'll have t go from 0 to 10. Again, Mathematica has pretty much done all the work for me here. I will put some axes labels in. I'll say that's time t. Actually, I'm going to be a little bit lazy here. I'm just going to pull my axes and plot range in from the plots I've already made, because why make extra work for yourself? There we go. And I run this, and you'll see I get nothing to start off with. What's missing? All right, well, I haven't actually defined what x of t is. So to do that, I am going to plug in my solution. So my solution has some rules that tell me what the x of t function is. So I am going to replace x of t with my solution. And then y, oh, I actually need to run it because solution's blue. So let's rerun that once. And let me quit kernel so I still get the general solution there. We'll just do this one more time. Don't let me down. There you go. Now I'll define my constants here. So we'll keep them in the original cell, but define them down here, and I should get my chart. And you can see there's your chart. As before, we can always change parameters here. I'll change my amplitude to make it a little bit bigger, make it nicer to look at. And if I give it some initial velocity, that'll, oops, that's probably too big. You can see all of a sudden it's no longer quite at the, it's a little bit phase shifted once you add that initial velocity. Once I have this, I can plot whatever I want because it's really easy to do. If I want to plot the velocity, I can plot x prime of t. That'll be the velocity, and I should change my axes labels. Change that to v and change that to meters per second. That's my initial velocity, and you can see that that matches up here. Here your x is decreasing. You start getting velocity values that are negative here. I can also plot, if I want to, let's see, I can plot, if I want to, I can plot a few different things. I can plot, I can start plugging in equations for the kinetic energy. I can plug in equations for the spring energy, 1/2 k x of t squared. And I'm going to square these. There we go. Square this one. And I can plot the total energy. So this is 1/2 mv squared, which is your velocity, 1/2 kx squared, which is your spring potential energy, how much energy is stored in the spring. And we've got your kinetic energy as well. Now let me change this to energy before I plot it. And we'll make the energy in joules. And let me get rid of the plot range because this should take care of that for me. And you can see you've got you've got all your different solutions there. I'm going to try. I'm going to evaluate this first because I think when I put the / solution in there, I think it's wrapping all those solutions into one. There we go. The evaluate just helps it separate what these different functions are. And if we want, we can put a plot legend in here. Plot legend goes to, let's make it a list. We'll say we're plotting the kinetic energy, then we plot the potential energy, and then we plot the total energy. There you go. You'll notice that energy is conserved. It's just a constant line here. The total energy is anyway, which it has to be. Whereas the kinetic energy and potential energy both go up and down, but they go up and down out of phase. So we can't actually, when they sum together, you're adding basically a sine squared and a cosine squared, which adds up to a constant, which is why you have a constant total energy. So that is how you can solve very quickly with DSolve. Again, it was really just one line of code that we used to make that solution. Mathematica is great for that reason and allows you to solve fairly complex differential equations very easily. Well, that is it for this time. Tune in next time where we will start further exploring the simple harmonic oscillator and other things that you can measure. Bye for now. And if you like the video, certainly click the like button. And if you'd like to see more, subscribe. And we will see you next time.